I'm glad we had that problem of hitting that boundary, and not so glad, because essentially you may think the code is fishy. No, the code is not fishy, essentially just that there is a numerical sensitivity. Now, what you would need to do when you're running your code, you would have to do additional processing, meaning that actually if you in previous stage were at, say, in the 5th set, then you expect to be in the 4th set. So when you check this inclusion for the set x4, you check it with epsilon, so there might be some problem with the numerical mismatch. Okay, so that's one of the things that actually might have happened here. Now let's actually be a friendly, and I'll ask you to select the. You can select the initial condition. Okay, this girl that likes to ask questions. Okay, you can pick any point inside of this big set. I mean, you can try the points on the boundary, but I'm not going to guarantee that this toolbox will give you numerically correct thing. Presumably it will, but we can check it. So what would be the initial? I mean, by the way, are you testing the code yourself? Is it behaving the way I'm showing?
Yes.
Okay, so it's a consistent. It's not. I mean, it's not me plotting some things random. Go on. -2 and 1. Okay, -2 and 1. Okay, that's going to be only a few steps. Okay, so in your code, essentially, there is this part exe online talk. So you just change the initial condition, -2 and 1. Okay, and if you run this, all right. So not so much of excitement, yeah. So from the essentially what is telling you? It's telling you, okay, your state is in the 4th. I can push it in the 3rd, then I can push it in the 2nd. Actually, in the 3rd, in the 2nd, in the 1st, and in the 0th. If you plot down k, now you can, by actually just doing x, you get x trajectory. You get a u trajectory by u, and k, you get a k, 3, 2, 1. So the state is controlled in 3 steps to the origin. Anybody else? Let's do 2 more experiments, and then I'll ask you to program backward reachability. Let's go for the. Who is the new guy? Who has arrived today? Okay, you pick initial condition from the set. Let's see how interesting behavior you get, or how interesting trajectory is.
So right now I'm not able to run the code yet.
Did you install MPT Toolbox?
Yes, I've got MPT Toolbox, but currently it says polyhedron can trigger undefined function or variable. And
is your MPT initialized? Can you just go to your MATLAB and type help MPT or something?
Okay.
It looks like you don't have it. Oh, no, not help of MPT, just help MPT.
Yeah.
It doesn't seem that you have installed. Okay, so you can pick an initial condition. The other guys can check it, and we'll see if you have installed the MPT Toolbox. So what would be the initial condition you want to control?
Let's go with 0 - 4.
0 - 4, okay. So anyways, I mean, after this I'll let you play with this as you like at a later stage, but we'll go to the backward reachability. 0 - 4. Okay. So now, this k is essentially number of steps you need to control. It stores it at any point in time. If the code runs correctly, if there are no numerical problems, it should form decreasing sequence by 1 until it hits the 0, and then it stays 0. So in this particular case, it is fine. And this is interesting because for this very same example, you do hit the other extreme point of this set, which is lower dimensional, and somehow it tells you it's okay. So in either case, all what I'm trying to say, your code has to take into account that there are possibilities of numerical inaccuracies. And this can be twofold. It can be from the machine precision, it can be also from the precision used in the toolbox. So you have to reason what happens. Okay. So what I would like you to do now, there are 2 things. The first thing, I would like to do just the backward reachability. So that was the part of the That was the part of the second lecture. And that's going to be presumably simpler exercise. Second part of the first lecture. Right. All right. So essentially, in order to implement this, how would you do it? So what I would do, if I were you, I would create a new folder where I would copy over these files. I would call that folder reachability. Obviously, in this case, because system is autonomous, you would have system.a, system.b. You would have a constraint structure c.d, target, etc. And then essentially this one-step backward reachable set can be obtained directly by just modifying the either preimage, restricted preimage function or one-step controllable set. Okay, so all what you would need to do, you just extract the proper matrices and multiply. In fact, actually, if you take restricted preimage function, rename it, you can generate this. So the way to construct this function is you just augment the matrices C. Below C is GA. On the right-hand side, you have a D, and below that it's H minus GB. So if you look at the restricted preimage function, you're just modifying that function to get one step backward reachable set. Okay. And then that function essentially gives you the iteration on the backward reach sets. So we can then, for the end step, we can just update. But okay, let me. So, shall I leave you 5 minutes to construct that function? Yes. Is 5 minutes enough? I mean, given that you have everything already there in the code. Okay, I'll check with you at 2:30. If not, I'll intervene with Adi. So just take the, essentially in the preimage, in the restricted preimage function, you have these matrices. There is no part with the control. You can get rid of that. And all what you need to do, your matrix M is going to be C semicolon GA. Your matrix L is going to be D semicolon H minus GB. And then you'll say that X is a polyhedron of ML. And of course, you call that differently. Okay. So what I'm saying is the following. So you will form the matrix M, which will be C, GA, L, which is D semicolon H minus GB. Of course, now in your case, C is a constraint dot C, D is a constraint dot D, G is target dot G, A is a system dot A. Okay, you'll need to construct this data structure in the data file as well, so, but modify that one very minorly. So I think it might take more than 5 minutes. And once you have that, you'll just say that X is polyhedron ML. Okay. So you will return this X, and that would be your function X equals B of X. B of XF. Okay. Or more generally, we can think of this as a xk plus 1 equals B of xk. Okay. So, do you have enough information how to do this?
What should be? What should define be? The same value as.
Beg your pardon?
What values should we assign to system.b, or should we just wait?
Well, I mean, for the time being, you can have an arbitrary matrix. At later stage, we can actually create the example. For the time being, just create the code which does what it should do, and then we'll see the effects of changing the data. So, I don't know, I mean, you can use the data you have, just modify it appropriately. You can say that, for example, you can take Okay, so take for example for x, first coordinate less or equal than 10, greater or equal than minus 10, the second coordinate between minus 1 and 1, for example, or between minus 2 and 2. There is no u. For xf, you can say that actually it's box minus 2, 2, minus 2, minus 2, 2. And for a, for example, generate a random matrix 2, 2, and b put 0. Sure.
So in your previous example, c was a constant term. Now c is
Now b is the constant term.
b is the constant term and c is the
No, c,
There's-
small c is
Yeah, but this is lowercase b. It's not uppercase b. And it's uppercase c. It's not lowercase c. So you have to change it. When you go to data, so that's why I'm saying the best thing to do is copy the functions to a new folder, call it reachability, modify the data file accordingly, and start modifying the other functions. You don't want to modify the functions in the same folder because then you mess up everything. And then at later stage, when you get the time, when the course is done, you can actually create your own library out of this pseudocode. But I mean, I'm not going to create that library for you. I'll give you the blocks and then you can create it yourself at a later stage. Okay, so I'll just help you a bit. I'm contradicting myself, but what can I do? Okay, so okay, so essentially what you're saying, you can say for a random of 2, 2, for example, for the time being, and then we'll add some example. There is no uppercase b, there is a lowercase b, 0 to 1. There is no c. The constraints now have a c and d. Okay, so there is no need for these two. Now, what did we say? There is no d. This is d. What did we say? We said the first coordinate goes between minus 10 and 10, and the second one goes between 2 and 2. Minus 2, yeah? It's that. Okay, target set can be everything. We are not going to have a 0, but we are going to have everything between 2, yeah? 2, 2. Okay, so that would be the setting. We have a number of steps. Now, if you take this restricted pre-image, what you're going to pass? You're going to pass the system. You're going to pass constraints. Let's rename this. First, okay, I want to save this. Save as reachability. I'll call it B set, backward reachable set. B set. Okay, you have a system constraints target. Now, if you look at what's written here, you have a constraint C. Now, you have a constraint D. You don't have a constraint D because there is no U. You have a target G times system A, and now it's going to be a lowercase system B. Yeah? Now, let me see if I got this right. So, no, I don't think that I got this right. I did get something wrong.
You have a GB in the M matrix.
So this is not here. Okay, this goes away.
Search for it.
This goes here, and this should be called D. Yeah?
You can install it from, but you have to use the installer.
I think this should do the trick. These few lines, yeah.
See the data file
At least read on
for the target.
Yeah.
Okay. So it's a constraint C, then target G system A, L is D, target H minus G, target G times system B, and then polyhedral ML, and there is no the plus, yeah? And I call it B set. So this function B set corresponds to the function you had, which was called the C set. Okay. Now I can close the B set because I don't need it. I won't need a control set, I won't need a mecha, I won't need optimal control, I won't need exe, At least not now. I can leave that because we'll multiply. Okay, we'll need n set b. Okay, let's call this. Now I have to get. Okay, so you want to see the things in the magnifier. Shall I leave it? You can compare your code. But again, I'm saying this is not the most efficient code. This is just the code to illustrate the things. Okay.
What's your data?
Huh?
How is your data now?
The data, sure. You can look only at the first example. Okay, second example is not changed.
What were you using in the first example?
Okay, so that's the data. It's a random system, okay? We'll fix, I'll give you matrices. For example, tomorrow I'll upload the data with more exciting matrices you can test. For time being, we can do. So what it says that the first coordinate of the x is between 10 and minus 10. The second coordinate of x is between 2 and minus 2. Actually, minus 2 and 2, minus 10 and 10. The target, you want to go between minus... Okay, so let's make it actually minus 2 and 2, for example. Okay. Okay. The next thing you want to code up is the n step one. Okay. So save as. And I'll call this and be set. There won't be z. There will be only x, system constraints target, and I think what we should do is just do this. Okay, and that's the n step backward reachability. Okay. So you're just calling n times one step backward reachability with the dynamically updated target set, yeah? That's what you're doing in the first two lines. Yeah? Okay, so you're catching up on this one. Shall we try an experiment? Now let's do this we'll call this now, let's change this name, save as, let's go to reachability. Now this was called exe offline backward reachability, let's call it BR. Okay. Now we don't want the, and it's going to be B sets, I suppose, or B set, what did we call it? Okay, so I should change the name. So it sets. Okay. So I think this should be that. Now, if everything is right, presumably this has computed something, okay. And if you look at the axis, okay, now we can plot this axis. I don't know how it's going to look at. Okay, so it's not much of the, okay. So this possibly sets overlap each other. So there seems to be some convergence, but is it that fast? Okay, so you start from a difference. Okay, so you start from, so in few steps it seems to converge. Now I did mention to you that when A is strictly stable and the constraints are bounded, the convergence will happen in finite time. Now let's just test the eigenvalues of the system dot A. So there essentially it's almost contraction with a factor of 0.6. So it converges relatively fast. After 5 steps, this becomes a very small number. Okay, so an x, magnitude of x is 10, so it makes it very quickly small. All right, so that would give you the nth step reachability. Now, interesting thing is actually as you run this, you'll actually get the different. Now, maybe you want to have a view sets. Huh? This is just essentially a nicer way to plot these sets. Let's see. But I'm not so sure if this is monotonic. This works when the sets are monotonic. Okay, so change the folder. Okay.
Your target.
So the target is -2,2. Yeah. So, all right. So how would you view? Okay. So how do we figure out if you want to plot a target? So what do you have? You have a target dot A, target G, and target H. Yeah. So it's between -2 and 2. Let's actually create a target which is equal to the x that will be needed for invariance. So 10, 10, and if you run this again, and if you then presumably plot this, let's see if they're monotonic. Now the trouble is it's reversed order, isn't it? Okay, so they're monotonic. You start from the outer set, you're getting the smaller bits and pieces, and it seems to me that it converges to this inner rectangle. Yep. So if you go from the whole space, which is between -10 and 10 in first, between -2 and 2 in the second, this is x0, x1 is this kind of shape, then you remove this corner. But actually we can do something else. Presumably we can, okay, let's do the following. Let's see the iterates as we plot them. Let's pause them. Pause. Okay. Now this is something I was hoping you would be playing. So this is x0. Okay. You generate x1, you get this set. You generate x2, you're removing further corners. You're removing the points which are bad. Here you don't have uncertainty, but here dynamics dictates that actually these initial conditions would leave the rectangle under A. You remove further points, further, and that has converged. Now, this is still the finite. Backward reachability without uncertainty. Okay, and okay. So, did you code up these things? Can you recreate the?
Where was it that we changed the? You said something about the wrong way.
So when I was plotting the things,
Yeah.
now when I start from a, okay, so if you look at the, okay, so this is the thing. All right. Actually, this is it. Okay, what do we know? We know that xk plus 1 is a subset of xk. So if I want to plot bigger set over smaller, then I won't be able to see the smaller set. It's gonna, so that's why I'm just indexing. So you're plotting the smaller sets on the bigger sets, and then you see both. That's all. And the other way, the inclusion was from inside outside. It was the other way around. So when I was doing controllability from origin, they were growing. In this case, they're decreasing.
Yeah.
All right. So this would be now essentially, so effectively what you can do with a one-step backward reachable set, you can actually iterate these dynamics. You can do n step with the other function, But now, ultimately, what we really want to do, we want to construct this object, maximal positively invariant set. And now we would need to change our code. Okay. The reason why we would need to change our code, we would need to know if this condition holds for some k. Now, what I haven't told you, in general, this may or may not hold. But what I did tell you, when A is strictly stable, and when constraints x are compact, I'm saying this finishes in finite time. So there is a guarantee that iteration terminates in finite time. This condition will be satisfied, theoretically. Now, again, we might have a numerical problem, because essentially, as you've seen in that simulation, when something is on the boundary, you may have a problems with the epsilon, because it's never zero, really. It's smaller than some number, and that's where you can get the discrepancies. So how would we... Okay, so if we have a function for generating these dynamics, and if we know that this would be termination condition, how do we generate a new function which actually gets this maximal positively invariant set? First, you wouldn't have a for loop, you would have a while loop. The condition would be precisely this condition. Now, how do we check this condition in the MPT? Last time I checked, I hope it's still the same. Now, we have these x, which are backward reachable sets. We know they're decreasing, yeah? Which means x of 10 should be smaller than x of 1, yeah? And it's true. So testing inclusion is just essentially using less or equal. So this is the inclusion which I was saying you can implement by using linear programming. But with this toolbox, you don't need to code up this linear program. You just do a simple comparison. Okay, so that's why it's nice. Now, of course, to make sure that actually I'm telling the truth, you can check the other ways. It should give you 0. All right, so you have a tool. Now, if I go back to the iteration, you have a tool to implement this recursion. Okay? So that's your B set function. You have a tool to test this condition, which is termination condition, and you just need to generate a function which will iterate until you satisfy termination condition, and which will give you the result of the iteration. Now, theoretically, you know that these sets that you're obtaining are monotone in one sense, in one way, meaning that each iterate is smaller, being a subset of the previous iterate. And if it happens that for some point you get reverse inclusion, then the sets are equal. You may expect some numerical problems with testing this condition, but presumably, let's hope it's not going to be as bad. So, you have a tool for generating these dynamics. This is your termination condition. You can generate a function which I would call maximal. I would call it MPIS. Okay? Maximal positively invariant set. You pass the same arguments you pass to this n-step backward reachable set. You run it in a while loop. One thing I would add, because you don't know how many steps this might run, I would add the maximal number of iteration as an additional termination condition. And I would add that as an input argument to your function. Okay? Are the instructions clear enough for you to code up that function? So let's do that, and if you do that, we'll move to the maximal control invariant set, which would be about the same. Okay, so the easiest thing is if you take this n-step and b-step function, and now I would call this MPIS. MPIS, system constraints target. I wouldn't put n, I would put k max, so maximal number of iterations. Okay, now I would have something like k equals 1. K is k plus 1, we have k equals 1, x of 1 we have its target we have set to be x. Now the condition you want is that, what's the condition I said? Xk xk subset of xk plus 1. So, while xk plus 1 is less than x of k, run this, okay? Now, of course, you may like to have or k is less or equal k max. Okay. And I think this should do the trick. Sure.
But you want xk undefined in the first iteration?
Say it again.
Should switch the lines.
Xk plus 1 want to be
Oh, it's not closed, yeah?
want to be undefined when you start with k equals 1 and only have defined x1.
You're absolutely right.
The first iteration will be checking whether x of x2 is more than x1.
You're right. You are right. You are absolutely right. That's why I said you should program this, but using the same functions, not me. Okay, so I wasn't as smart as I thought I would be, because I need two sets to compare to begin with, yeah? So I have to replicate some of the code. H of I, okay. Now there is another problem because I'm iterating. Now this is k plus 1. Let's get some logic to this one. Okay, so this should, now it's not k, isn't it? It's just x of k, yeah? Now, will this work? Will this work? Assuming the numerics works. I beg your pardon?
This is supposed to be k. Current target equals x of k.
K less or equal than k max.
Find the first, because I don't think you should increment k outside of the loop. I think you should only define x1 and x2 and then start k at 1.
Okay. All right.
I think.
All right. I'm actually going to do it the way you like it. This way?
No, define k to be 1.
Well, I mean, if I want to run a loop, next time I compare, I need to compare, so the k has to be 1, yeah? Actually, what you're saying, I need to have different thing here, yeah?
Yeah.
K minus 1, this is what I need to have. Okay. So see, you confuse me with saying k plus 1, this and that. Anyways, this is something, I mean, this is something I want you to code out. I'm pretty sure I can do this as an exercise when I get free time. But this is your exercise now, and it's your feeling to get the shape of these sets. Now, I don't know if I did this well. Let me see what's the target. Okay, so that's fine. Now let's put k max. Let's limit this to 100 iterations. I don't know what system A. So this is not stable. So this wouldn't terminate in finite time. This random matrix we got. So that means that essentially, okay, x. So it doesn't seem that I'm getting stable matrices, huh? Alright, so now we have unstable.
Is the current target constant or does it change between?
Which one?
The target is a constant during
In the loop, yeah? So it has to change.
Yeah.
Actually, there are several problems with this one. This is not I, this is 1, this is 1. Yeah? And this one has to be... Okay, so let's see what we have. So this one would have to be k minus 1, yeah? Alright, so you're getting engaged. We are getting somewhere with this code. Eventually, within another 5-10 minutes, we'll get a code which should work. Alright, anything else? Okay, so let's for an experiment, for just our amusement, let's actually remove this k-max thing to see if that's a smart idea, and then we can add it. All right. So I think now we have a good, in terms of a kind of, all right. So I have an error. So where did we get it wrong? So we have an extra bracket here. Okay. Right. Now, so we don't have this k max, and essentially this thing may be looping. So the k at which it iterates, it might be quite large. Yeah. So it doesn't seem to be a good idea for numerical purposes not to have a maximum number of iterations you are allowed to give. So it seems to me that okay. So it seems to me it makes sense to return k-max, but let's check once again. System A, egg offense. So this is fine. Now, did we get all this right? So case 3, it's 2, so this is x of 3, is that? Okay. So it should be fine, yeah? So you do want to add this k max. And you do want to have or k less or equal k max. And now if we call this one, let's say we allow 100 iterations. Sorry, what am I saying here? What should I have, or end? I should have end, not or, yeah? So, let's see, view B sets. Oh, this is amazing. Okay, so now the sets are monotone. The other way around, yeah? So what was the... plus 1 plus I minus I plus 1, yeah? Minus I plus 1. Alright, so now this has converged apparently. So go backwards in time. But this is very strange actually. So now what I had was okay. Now what is the problem? Okay. Now, okay, so it seems that this has converged in the second step, but for some of the reasons, and this is what I was afraid, that actually this condition fails. Okay, so testing this inclusion, so you have x, so testing apparently inclusion x of 2, x of 3 less than x of 2, it tells you it's true, well actually it seems they're equal. So this is the numerical problem we have. Okay. Now when you plot these sets, they don't seem to be distinguishable, are they? So how would you solve this issue of actually comparing the, so there seems to be a problem with this condition. X of k less or equal than x of k minus 1. Now, this is interesting. So essentially they are equal. I don't know how they implemented this. So if you check now x of 2, we know x of 2 is less than x of 1. Now, is x of 1 less than x of 2? It's not. What about, okay, so I think actually what we're gonna do, x of 3 less than x of 2. Did I reverse the sign here essentially? So, well, xk is a higher, we know it's a smaller, so it has to be reversed here. Why didn't you correct me for that one? Huh? All right, so now it works, yeah? So I had a condition differently, yeah? All right, so you're not paying attention as much as I thought you do. Okay, so now we have something which supposedly works. Okay. Huh? Now, what else do you want to return from this function? What you would like to know, you would like to know when did you stop, yeah? So you can call that DI, determination index. Or, okay, so you can say, yeah. Now, of course, this thing. Now, what's the problem with unstable A? Why do you think things will not converge if you have unstable A? What did I do now?
The argument is just max, not k-max.
What did I do?
You need
Oh,
grade.
I need a number, yeah? But that's what I thought. Okay, so this stops in 2 steps. Okay, I mean it's now you have a tool you can play with. I do want you to make you aware that this condition, that's actually condition for inclusion the other way around. It's this condition. Of course, I mean awkwardly enough, when I write here I can use 0. When you index things in MATLAB, you can't use 0. At least I don't know if you can use it in the new version, but when you generate, you have to start from 1. So what is x of 1 is my x0. So that's why you have this nasty mismatch k plus 1 and k. In any case, this is the condition. So one of the problems you may encounter when you implement this iteration is that actually this condition may fail numerically. Even though it holds, your numerics may report it falsely. So that's something to keep in mind. For a more sophisticated case, you would need to analyze this much more deeply. But for simple examples we play with, I think the toolbox should be fine enough. Now, for these sets to be non-empty, the condition was that you have an equilibrium point. And in that particular case, we had the constraints between -2 and 2 and 10 and 10. So 0 was inside of this set. Zero was inside of this interior of the set, and because the system was linear, that point satisfied this condition. That guaranteed that all iterates were non-empty. So everything we computed was well defined.
Did it run?
Yes. Okay, so my code, finally, which I corrected with your help, which looks something like this, terminates in 2 steps for this. Now, there is a problem because we are generating random matrices. Everybody has a different matrix. Now, because everybody has a different matrix, you'll get different results. Now, before you run that function for computing the maximal positive invariant set, I said many times it terminates in finite time if you do have strictly stable A. So if your random matrix happens to be unstable, I cannot, or algorithm cannot, not me, algorithm cannot guarantee that it will terminate in finite time. With the use of K-max, you're actually going to abort at one point when you reach the number of computations you allowed, or number of iterations you allowed. And at that point in time, you can examine what's happening. Now, of course, if you have, for example, matrices like identity, this is not strictly stable matrix, it's only stable. You terminate in 1 step because set doesn't change. Any set you take, it becomes. So the condition for strict stability is sufficient condition for termination of this iteration. Sure.
Was the inequality the wrong way?
Yes, yes. Well, actually, I didn't make all mistakes because I don't know how to code this. I made some of these mistakes to keep you engaged in the coding. I was hoping you would jump on saying that's wrong, and so on forth. And some of you did, so I think it has succeeded.
So it's,
Check your system matrix.
yeah, it's fine.
Okay.
It's supposed to decrease with the notation, right? So x
Now, the speed at which algorithm converges will depend very much on the eigenvalues. So essentially, you can link the largest eigenvalue of the matrix A to the number of iterations you have. Now, in some of the papers I've given you in the Google Drive, there are estimates in terms of the ln. Let me see if I have uploaded that paper. I'll tell you what specific papers actually are very worthy reading in this respect. Actually, this is the wrong one. Okay, so this is an excellent paper to read for the computation of maximal positive invariant set. It actually gives you much more generality and much more details than what I described. For the robust case, there is extension in here. Now, I was wondering if I gave you my paper and it doesn't, not minimal. I'll actually upload one more paper which would be interesting, which gives you these estimates. Let me actually dig it up. Professional publish papers, conferences, sort me out. Okay, so actually here is a paper I wrote which would give you the quite detailed overview. Okay, so you can actually estimate number of iterations. I think there was an ln formula, I wrote it, I think so. Okay, so I think actually you can work out that formula using ln from here. Okay, so there are some numbers you can estimate and then you can kind of get an estimate for the integer using ln, because you have to bring it down from the exponential. But I thought actually it was written explicitly in the paper. Obviously, I don't keep everything in mind. Okay, computational remarks. These are the things. Now we can test some of these matrices for your code. So you can take this matrix, for example, and you can take the same constraints. We can all test with this matrix. Now this matrix is kind of interesting because it's a very slow contraction and it's a rotation, and because it rotates you need a lot of hyperplanes to capture the trajectories, as you can see in the figure here. So this is with the disturbance, that would be the next step for you to code up. But the same behavior of having this kind of almost elliptical boundaries will appear in a quadratic kind of. Okay. So I'll actually upload this paper later on. I think it might be useful. If you like, you can generate second example using the same constraint set, but using this matrix A. Do you want to do that? And this is the one that actually you've seen in the videos before.
How do we interpret the result we get out of this function? It's an array of two polyhedra.
Sorry, for a moment I didn't hear you. Can you say it again? No, it's okay.
The output of the function is an array of two polyhedra.
That's correct.
That's okay.
So the output would be array. So the last term in this array would be your maximal positive invariance set. I think essentially the reason I brought you do all these computations and actually storing it for these pseudo examples. What would you return? You would return only the last iterate. That's what you need to use. Yeah. That's a good question. That's yep. So because essentially at that point in time you know that xk is equal to xk plus 1, so you don't have to carry on any further. Okay. But because we computed all, essentially also for illustration how these things evolve. Now let's try this matrix. I mean, I guess one of the things is just to take it and try. And fingers crossed it does work. You never know. I mean, this computational geometry can be quite messy because it might like some numbers, it might dislike some other numbers. So I hope I did put this right. Now, of course, you can generate a small code which does.
Can we see the matrix?
Sure. You want it from the paper? I think it's easier to see. Yep.
Can you scroll down again so it gets higher on the screen?
Down or up?
Well, yeah, the thing.
Oh, is this one you're using now? I think that's different from the one.
Okay. Just make sure when you copy to the MATLAB that you actually put semicolon. Okay, so here we also have a constraints, yeah, for this example. So let's take these constraints as well, yeah.
Give us a sec to write down.
No, I'm not going to change this. I'm just saying let's use this constraint set. So modify the. So you will have 70, 30, 20, and 10. Okay. So let me know when you're done. So are you getting any of these sets? I mean, for the previous example, for your random matrices, is it converging or not? Is it stable? That indicates your matrix seems to be unstable.
Is there no B here?
Check eigenvalues of your system matrix.
Yeah, the 1.
What's one eigenvalue?
Yeah.
It's unstable. So for unstable, there is no guarantee that actually. I mean, if you were able to find a complex set which can find the trajectories of unstable linear system, that would contradict the instability. So it's not possible to have eigenvalue which is greater than 1, and then find complex subset, full dimensional complex subset which would contain the trajectories. Finding such a complex subset would guarantee that the trajectories are bounded. And because you have eigenvalue greater than 1, that's not possible.
Which target should we use?
So this is going to be, the target is going to be x.
Okay.
Because now we are computing the maximal positively invariant set. When you are computing maximal positively invariant set, your target set is x, the whole space.
Okay, so it equals the constraints?
That's correct.
Yeah, okay.
That's, so did you copy constraints and the matrix? Can I copy them myself? Okay. All right. So this should be 70, 30. $20, $10. Of course, you don't need this number of steps for the other function, but it's there for a finite. Okay. Now, what did I want to add there? You interrupted me. I wanted to copy this, didn't I?
Use the same target set as last time?
No, the target set is the state constraint set. So it is equal to the state constraints.
Okay.
It's equal to this one. Okay.
Can you show the constraints you used again?
Sure. Okay, so if you look at the constraints, so 1, 0, minus 1, 0, 0, 1, 0, minus 1, that's a matrix C. Matrix D, 70, 30, 20, 10. The same for G and H, yeah? Okay? 70, 30, 20, 10. Okay, so here we have a K max equals 100, for example. I don't know how many iterations you would need. And let's call this exe MPIS small script which illustrates this exe MPIS. And then we can add this view B sets. We can add view B sets. And now in the B sets we can actually, we have a pause so we can see what iteration has done to the sets. Okay, fingers crossed it works. Right, okay. All right, it has done something. Well, this apparently has converged in 2 steps without uncertainty. This is very peculiar. Okay, so let's see. Max is 100 data. Did I change anything? Let me see. I don't know what I've done. Okay, so there were how did I manage to get this to be? Did I copy wrong? Did I copy this wrongly?
If you run the NV sets and then run V sets, you see that there are supposed to be a lot more.
There's supposed to be
more.
Okay, can you actually? So which one?
But the MPIS function still returns 2, even though.
So that's what I was saying about this inclusion condition. I don't know how the toolbox behind does this equality. So there is an epsilon which is involved. What I can do, I can try to use equality instead of less or equal. But I would imagine actually if you have equality as a condition, two sets being equal, I would imagine that's more numerically sensitive than actually having, because you know inclusion from one side. So having inclusion from the other side is only one-sided test. If you have equality, you would have to check both sides. So I'm afraid if actually it has a problems with the numerics with one side checking, then actually has a problem with more complicated test. Okay. So what did you say? You said you run the...
Run the other set.
Okay.
You had. And then you run the view sets.
Okay. Let's see that.
And then see.
So this is okay. So this is precisely what I was expecting and which matches. So now I don't. Okay. So I don't like to do this, but okay. Let's see if that is going to change anything. I fear that actually. No, there is some other problem.
I think I managed to make it work by putting not equal.
Say it again.
I think it actually is able to set two sets directly equal. So if you change it to while not equal.
Oh, we have changed this. So essentially, while
Because now I got 22.
while not, yeah, this.
While not equal, yes.
Okay, that's what it should be. So run until they don't become equal. Okay, but I still don't know. See, I mean, I don't like. Okay, so there is one of the, that's why I was calling this pseudocode. I don't like actually going on and changing the code as the example behave differently. And for that reason, actually, you really need to understand very deeply computational geometry behind it. So it's difficult for me to know what precisely. I mean, I have my set of the routines, but I can't give you those. All right. All right. All right. For some of the reasons, more complicated test seems to work, and this defies my logic, because essentially we know by construction that inclusion is satisfied one way. So if we satisfy inclusion the other way, we know that the sets are equal. So now what you're saying is, that actually you didn't change to equality. Excuse me. You had it that way, but you just added not.
I changed from inequality to just directly while not equal.
Not equal. Okay. So this is what you get. So this is actually, I mean, you may think that this is, so this is essentially what you were doing, removing the things, and you may think this is a kind of simple shape, but actually, you know, this is only two-dimensional example with 4 constraints. You can imagine if you take higher dimensional system with many constraints that actually these objects may be quite complicated. Okay, so, all right, so we are getting somewhere. Now, anyways, this is supposed to be an exercise to illustrate how you do things. Then you can refine these codes and go further into that. Can you tell me now the following thing? Having this exercise done, would you know how to construct the algorithm for maximal control invariance set? Why not?
Because I haven't got the basic functions working yet.
Which one?
Well, NBR set. I think you're moving a bit too fast, like you're talking throughout.
Okay.
And then I don't know if my first function is working, and I still don't know.
Which function are we talking about?
Well, I think when step backward reachable set works, I have got the n step backwards reachable set working. So I haven't tested the.
So okay, so let me now. One of the things that you do want to look at now, this MPIS function, for some of the reasons, changing it to this condition helps.
I can't see anything. I can't see anything.
So okay, just one by one. Go on.
Could you please zoom in again?
I can't hear you. My voice.
Zoom in.
Oh, so you want it enlarged? Okay. And what was your question?
Yeah, same.
Okay. I mean, I was hoping you would be playing with this.
Yeah, but you're constantly changing, so.
I mean, this troubleshooting is something that actually helps you learn a lot. Okay? It's and it also gets you to appreciate how lucky you are that we have this toolbox. Imagine if you had to program all these things without toolbox. So this, what we wrote, not equal two sets, you would have to have a function for checking whether two sets are equal, which would essentially require you to solve a number of LPs or a large LP. So it would be additional work. So actually, nevertheless, even though we don't know numerical stability of this toolbox, we should be grateful to these guys that actually we can at least prototype these things very quickly. And again, I mean, this is not going to be a professional toolbox. You're not going to make money out of this toolbox. This is something just to get a feeling of how these things are actually getting complicated. One of the reasons why I want you to do this exercise is to see that even in very simple examples, the objects that we are after get extremely complicated. So even though initially you have a small number of constraints, as you look at a multi-stage problem, this number of constraints gets propagated through dynamics, and actually it gives a rise to very complicated shapes. So therefore, your optimization is not necessarily as simple. So what do we do now? I give you a bit of time to clear up this function NPIS.
Well, can I see the B set function? Well, can I first see the data that you use for the
What do you want to see?
data?
Okay. Okay. Okay, so let's do this.
Is the G matrix supposed to grow for each iteration?
Yeah, that's what I was saying, that actually you're stacking the inequalities. So the number of constraints grows. Now, I'm not so sure if the toolbox itself removes. If you remember previously when I was explaining that actually you have a number of constraints which can be removed. If you go to the figure, can I get rid of magnifier for a second just to illustrate this point? Okay, so if we go to the figure, so this is exactly what I'm saying. So if you look at, if you look at this set, this inequality is completely irrelevant. You don't need to keep it. So this one matters. The other ones all matter because they describe the boundary, but that one doesn't. Also, this one doesn't seem to matter. In this particular case, it doesn't seem like a lot of saving, but this is a simple example. In many cases, there will be a number of inequalities that actually they increase dimension of this matrix, which, if the toolbox is done properly, each time you do iteration, it would remove such constraints because you don't need to propagate them. You don't need to start increasing dimension of these matrices for no good reason. Okay, now I'm coming back to the code. So, what was the question?
Can you run B set on that data and plot it?
B set on?
On the data you just showed me?
Sure. Okay. What do you want?
Can you just plot it?
Now, why does this magnifier doesn't like the figures? So
I just press.
okay, so actually it does like it, but okay.
Okay, that's working.
That's what I got. Oh, you have to be a bit more confident in yourself.
I just wanted
I mean, the fact that actually it checks out at you have to do this. How would you now actually? Okay, so obviously at this point we are relying numerically on the toolbox we use. It's a fair point what you're saying now. How do I know what I'm computing is correct? And this is where actually part of this course enters into computational geometry. And that's what I said, actually it's really matter in its own. Generating these polytopic or polyhedral objects is entirely field on its own research in computational geometry. So typically there are many things that you need to consider, and that's why I was concerned about, for me it's temperamental behavior, that actually simpler condition for terminating the loop fails to work while more complicated seems to work. Okay. So now, can you explain to me why do you have this kind of asymmetric shape? So, in other words, it seems to me at the bottom you're cutting out bigger chunk of the set, while at the top you're cutting out the smaller. It should be relatively simple to answer if you look at what your original constraints are. It's this box, yeah? So, because the original set is asymmetric, the iterates need not be symmetric. Okay? If you remember in the previous case, we had a kind of symmetric scenarios, so you were cutting out equal shapes. Right? Okay, so what else do you want to test?
The R set,
Which one?
the one step backwards, no, n step backwards.
All right, that should work. I'm not used to this magnifier, okay. So what exactly you want to do about those sets?
Can you just zoom in?
Oh, you want to check the function.
Yes.
It's very much like the controllability.
But can you go back to the B set?
Am I being examined? Am I being examined here, or
Yeah.
you like
I
it?
don't know what's not.
So what is not working?
I get a reference to non-existent fields.
Okay, let me see.
Du tar bort den parentesen der. Det kan du ta bort.
So is it working for you guys?
Yeah.
All right, so,
It's working.
okay, sorry. Let me see. So which one?
So I get that one, but when I call the
Oh, so
NBR set, I get a reference to non-existent field C.
you have NBR set. That's how you call it. You're not calling it NB sets.
No.
A BR set, current target. Okay, right, integer. Constraints, that seems right.
Yeah.
Now, what does it say? BR set line 5. Can you open line 5?
Yes.
Constraint C. Can you actually just type constraint C outside?
Wait, sorry.
So it is there. Now, did you specify constraints? Did you type properly constraints in the calling the function? NBR,
call?
yeah. Okay, so if you go to the definition of the function, maybe it's typing error for the constraints. No, constraints, that's typed properly, yeah? Polyhedron target H.
Wait. There we go.
Jeg gjorde det forresten, det kan jeg, at det var noe jeg gjorde
Oh,
tidligere.
thank you. You solved it for me.
Oh, you flip the way you enter. Okay. No problems at all. All right, so we are getting some. That's nice. That's nice, actually, nice coloring as well. Okay, so I think there will be some pseudo code of yours that I'll be putting online. Now, the next exercise, and I really want you to start getting a bit more independent. Maybe I'm too demanding. So, having all these functions, do you know how to do maximal control invariant set? So, if you look at this maximal positive invariant set, okay, it would be very much the same thing, but essentially instead of using B set, you would be using function C set. Yep, that's all. And of course, you would do this in the other folder, in the controllability folder. Yeah. Okay. So, are you with me? Okay.
What was it called? The maximum.
Call it MCIS, maximal control invariant set.
Yeah.
And then when we do robust, we'll call it maximal robust control invariant set. And when we do robust positive invariance, maximal MRPIS. So, okay. So I think what I'm going to do with you Friday when we wrap up in the afternoon, we'll select some of your code to put in the slides for the code, and then I'll actually send you the links to this code. This will require me to copy the code. I'll also put your names next to the code. Now, once again, the point of this exercise, it's not that actually you master this specific code. It's more to illustrate and understand the concepts, and also to get you started on using these notions. Presumably now you have this set of tiny library or codes that actually you can improve and write up properly for your purposes at later stage. Okay. But I do want you also to get a feeling that actually computing these things, once you have the right tools, is relatively easy. Okay. So today I'm actually very pleased that actually you interacted with me on this one and that we managed to fix few. Thanks to your colleagues, we figured out that actually this toolbox likes more sophisticated constraint than simpler constraint, and it works better when actually you put harder constraint on it. I don't know why. It doesn't make any sense, because for me to test equality, you would have to test inclusion both ways. Yeah? And to test inclusion both ways, you would include the condition we had. Okay. All right. Now, how much time do you need to do the maximal control invariant set recursion? The guy who hasn't set up MPT will have to see how to do it. It works.
Yeah.
And these things also work at your end.
Yeah.
Good. All right. So, what do you think? How much time do you need?
10 minutes.
All right. So that's the final exercise for today. Generate the function for maximal control invariant set, and let's see iterates of the iteration. Now, one of the things, control invariant case is much more complicated. It's very difficult to guarantee that actually finite time convergence is going to happen. So you can use the matrices you have, and you can see what happens. I mean, still compactness of the constraints might help, but unlike the autonomous case in which actually strict stability will suffice with compactness for finite termination, in a control invariant case is a bit more complicated. But let's see what your code does. So in other words, what I'm saying, definitely have the restriction of the computations. Okay.
How should the answer look like? Just if you run with one of the data we used before?
I don't know. I mean, I haven't run it myself. The answer will look, you'll get sequence of decreasing sets. If you take a double integrator will add some rotation, so it might look very much similar to what I had today, but I really don't know. I mean, one of the ways to do it is to test the B steps. Okay, so if you go to that one, all right, so one of the ways to do it would be to change the target set to the constraint set. So the target when we ran was 0, and then let's see what happens. Okay, so let me actually see what is X. Error. Okay. So not. Okay, so it's inside of the. Now this actually doesn't make sense to compute the control here, because essentially you don't want to solve that. What we want to compute the control sets, yeah. And this is NC sets, yeah. Okay, so plot. All right, so this is very likely what your answer should. So now in the view C sets we can add the pose. And then let's see what happens with this one. This goes the other way around, yeah. So this should now, we should change the index, yeah. So this is what your answer should look like.
Can you, sorry, can you repeat the...
Now, let me see what happens here. Now, why this has complained?
Ok, så nu ska vi göra något. Ja.
Okay, so very likely here what happened now, we have taken point outside of the, okay, so let me see what are the, we have taken 0, -4, which was outside of the control set. Okay, so let's take the, so at iterates k is 0. Now okay, so the code I've written for you in the previous one actually solves the problem of minimum time to the origin. To the origin. The one I've given you, the tools. Okay. It doesn't solve the problem to the target set XF, okay? It looks to the code at the origin. The sets are nested one way then, okay? So that's what simulation shows you earlier. And the sets I showed you, now I've changed the target. I put the target the outer set. The shape of sets you get should be the ones you should be getting using this maximal control invariant set computation. So the shapes you're getting should be of this form. I don't know if they converge because this I've done just finitely many iterations.
The thing I got was that I got this figure, but then when I used the UC sets, then I got that it was outside of the...
So it was plotting the other way around?
No.
Let me see. Well, I don't know what you were plotting exactly, but let me see.
When I'm using this, or if I run the sample, and I get like this.
So that seems right as a computation.
Then I get index exceed matrix dimensions.
What is the C set? How far do we go in the C set? Now it doesn't have an n, so you have to put this determination index, or actually you can say that n is the size of x. Yep. So what changes? This function was plotting this n step sets, yeah, and in n step case we had n plus 1 sets. Yeah. Now, because you're iterating, it's not necessarily n plus 1 sets.
Yeah,
so I think one of the ways to resolve that is actually to put an index and exactly, and that should be fine. Okay.
Which data set are you using? Same as last.
Okay.
Excuse me.
Sure.
Can you repeat the problem? Which set are we going to calculate?
So maximal control invariant set. So you're effectively using the same function as the one for the maximal positive invariant set, but you're not going to operate with a backward reachable set operator. You're going to operate with a controllable set operator. So effectively, you can use almost identical code, but this will be C set, not a B set.
But you have to expand the model with
so,
or something.
But you already have that in the other folder, yeah? You already have those routines, so you just code it up in controllability folder, not in reachability. So effectively, if I'm not mistaken, all what you really do, you're just changing this for the C set and those for C set. Yeah. You're just making effectively 2 changes. But as I said, the issue of the convergence is not as simple.
Are you sure you're only exchanging it for C set? Because then effectively isn't the only difference the pre-image? Because the C set.
Yeah, but in a okay, so keep in mind what I did say. Okay, keep in mind. It's a very good question, but keep in mind the following. When you look at the one step backward reachability, the one step backward reachable set is equal restricted preimage. Okay? When you look at the control case, it's a projection of the restricted preimage. The reason is you have to project out U. Here dynamics have dependence on U, but it doesn't matter. What matters for you is this function C of x, which operates on your set iterates. So effectively in your code, you just change B set to C set. And of course, that code has to be part of the controllability routines, not reachability routines. Okay, so let me see what you have. Is it now working properly?
Yeah.
Is it converging?
Just
How many do you have index for determination?
7.
Okay, so it happens to now. I mean, you can change the constraints or do something, experiment, figure out different A's. So, all right. Okay, so everybody managed to get this routine running. Right. So. Is it working or not? We have one winner. One person has definitely solved it. There is another person. How many iterations do you have? That's DI, I think it's called. How many?
14.
14. How many?
7.
Are you running the same example?
I don't know which example you're running.
Just the data he gave us, example 1.
Example 1.
But I've taken away the 0 on the H target.
Maybe you kept the 0. Maybe you were doing from inside.
Oh, yeah.
I've taken that away.
Now, okay, just a minute. Now, an interesting question. So you have two different target sets. The iteration has converged in both cases. Do you think that in general this would converge to the same thing? So in other words, if you start going from the inside, the sets that you compute from the positively invariant set inside, they would be control invariant by construction. While those outside that you're computing, none of the sets is control invariant until you reach the limit. So therefore, a logical approximation would be to start growing from inside outside, rather than going from the outside inside. But the question is, will these two things converge to the same thing? Will they have the same limit?
Yes.
Right, okay. So that's the question I want you to think about, and you'll tell me the answer tomorrow. Okay, so based on one example, we claim it's true for all examples. Not quite convincing, but it's very nice to know it works in this example. So it's not necessarily false. We don't have a counterexample which disproves it. So for this example works, but sadly enough we don't have a proof which proves it that it works for all examples. So that's the question I'm going to leave you with until tomorrow. And okay, so tomorrow we'll go very briefly over basics of optimal control and robust optimal control, and then we'll start with the tubes really. So because tomorrow what I'm hoping to do with you in the numerical part of the exercises is to actually generate the robust versions of this code. So effectively we will be adding this extra step, which was actually computing these effective target sets to take the effect of the uncertainty. But all what it means, you'll be able to reuse all of your codes with a minor change. I mean, when I was creating these pseudo exercises, that's how I wanted to build it. Actually, as you go along, you reuse the code you create and you just make minor changes. And it gets you motivated to look deeper into this code and playing with. Now, what we didn't finish is how to construct the control for example, for invariance. Once you compute this maximal control invariance set, how would you construct the control to keep the state inside of the set? Well, the answer to that was relatively simple, because essentially what it says is that you're really computing just the one-step control map, and you have a function for that. You can say minimum effort control, where the target is the set itself. That's all. So in the other case, you were updating going from xk to xk minus 1. In this particular case, you'll be going from omega to omega. Okay, so you can reuse the function you have previously for the controls in the C case. Now, anybody else has managed to put up together this maximal control invariant set calculation? Are you getting the consistent results?
Yeah. I have something.
Okay, how do you compare if you have some? I think actually, I think consensus seems to be that we are converging to the sets I plotted. So it should be something like this.
What model is it?
So this is a double integrator, I think.
Okay, so I used the first one from the...
It's the first from the controllability part of the axis. So I think this is the kind of shape you're getting. Is that something you're getting? Okay. So 1, 2, 3, 4, 5, 6. Very likely that's the thing. Okay. So if that's done, I'll actually leave these few minutes for questions you might have, and then we'll call it a day. So, any questions? Okay. Now let me ask you one thing. Do you find beneficial to play around with the code a bit and to try to put these things together? I thought it would help you actually to visualize things and get the connection between the computations and actual equations, which you don't get too often to see.
Very good.
Okay. All right. Right. Do you have any questions? Sure? It's not Friday. It's still Tuesday. Okay. All right. So if no questions are there, I think we'll call it a day. And we'll continue tomorrow at 9:15, the same room. Thank you very much for your attention. Thank you.